Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. Our topic today, which will be the last lecture, is about well logging data integration. We will see how the logs and the logging data can be integrated with data which are not recorded at the borehole, because we have seen how the logs are helpful in distinguishing different types of rocks, different types of fluids, and how they are helping us to discriminate between reservoir and non-reservoir zones, to extract many details and crucial information about reservoirs, permeability, porosity, resistivity, radioactivity. So by the integration, we will see how can we extend the success which we have achieved at the borehole to areas which are beyond the borehole or the well location. But firstly, I will start by some basic concepts and terminology in order to help you understand the, the rest of the lecture. I will start by the stress and strain. Stress is defined as a force which is executed on an elementary area over a material or of a material or substance or a body. The, the strain is nothing but a deformation which is caused by the stress. The stress and strain, they are actually proportional to each other. If we increase one, the other one will increase. If we increase the stress, the deformation will increase, but up to certain limit. And this will define for us the Hooke's law. When the stress will exceed certain limit, we will have a collapse and we will have a failure of the system or the material. Uh, Medium is considered to be elastic when it will return to its original state after we remove after we remove the force or the stress or the cause of the deformation. And usually in seismic methods, we believe that the the deformation is so small that it does not cause a permanent deformation of the rock. So we are working in the elastic region. So all the seismic methods, they are working on the elastic region, and they are supposing that we're under the elastic theory assumptions. So in this area or zone or region, which is the elastic region, there is proportionality between the stress and the strain. And since we have different types of stress or stresses, of course, we will have different types of deformations, and this will produce different types of proportionality or relationship between the different stresses and different strains. And this will define for us the elastic properties, because we have different forces, we'll have different deformations, and the response or the relationship between those different forces and deformations will define for us different elastic properties. We will try to see them or some of them one by one. Firstly, we will go to the first bulk property or bulk modulus, or we'll go to the first elastic moduli. The first elastic moduli is the bulk modulus. The bulk modulus is nothing but measure of the body or the material resistance to uniform compression. So if we apply uniform compression over the material or on the material will have a response and it will be deformed. So how much this material is deformed is actually defined by its bulk modulus. Okay, so and the inverse of the bulk modulus will define and will produce or will give us the compressibility, or the compressibility of the material, or how compressible is the material, is defined by the inverse of its bulk modulus. We have also the shear modulus. Shear modulus is um, also called the modulus of rigidity, or the Lamy constant, and is nothing but ratio of the shear stress to the shear strain. And the shear modulus is nothing but a measure of material response or resistance to the shear deformation. The Young modulus. Young modulus is one of the very important elastic moduli. It is defined as the ratio of longitudinal stress to the longitudinal strain for an unconfined bar or material which is undergoing longitudinal compression. So if a material is subject to longitudinal compression, it will be deformed in that direction, and then the ratio between the stress or the force which is executed or which is causing this deformation to the deformation will define for us the Young modulus. And this will reflect the stiffness of the material or the earth materials. The Poisson ratio is nothing but the relationship between the shear modulus and the bulk modulus, and is expressed by another quantity, or in another way, which is the fractional change in width to the fractional change in length. So if we deform material, and this material will be deformed laterally and longitudinally, so the ratio of the, the lateral deformation to the longitudinal deformation will define for us the Poisson ratio. Now, the seismic waves. Seismic waves, you might have already seen them in general geophysics. And for those of you who have already taken Geophysics 1 or seismic methods, so you are already familiar with seismic methods. So seismic waves, they are very important component of the seismic method. So the seismic waves are kind of parcels of elastic energy that will propagate from a source, or from a seismic source, like an earthquake, or like man-made source, for example, an explosion, or maybe a vibroseism or a mass drop. So those seismic waves are classified into two types of waves: body waves and surface waves. Body waves can propagate through the internal volume of an elastic solid, and the P wave and S wave. The surface waves, they are very lazy waves, and they are not going very deep in the subsurface, but they will propagate only at shallow intervals, and they will come back again to the surface. Compressional waves, sometimes we call them longitudinal waves or primary waves or P waves. They propagate by compressional and dilatational uniaxial strains in the direction of the wave travel. The shear waves, they are different than the P wave, and they are propagating by pure shear strain in the direction which is perpendicular to the direction of the wave propagation direction. So those waves, they are causing some deformations in the material, or in the subsurface, or in the earth material. The P wave involve deformation that will include change in volume and shape. But the S wave, they will cause deformations which are affecting or are associated only with the shape, but not the volume. When a seismic wave or seismic waves P or S will travel through a material, or different materials will have different speeds or different velocities. Why is that? Because the velocities of those seismic waves, P or S, they are actually a function of the elastic properties of the material. They are a function of the bulk modulus and the shear modulus and the density of the material. But the S wave, for example, or the speed or the velocity of the S wave is function of only the shear modulus and the density of the material. So that's why the the S wave does not propagate in the fluid, because the fluid do not have resistivity or resistance to the shear deformation. The resistance to the shear deformation is zero, and the Vs is zero. So the S wave does not propagate in fluids. Now the types of velocities which we are recording actually in from the rocks, we have already seen that rocks is actually a combination of pores which are saturated with air maybe, or with water, or maybe with hydrocarbons, and also with a solid part or solid components like minerals which will form the rock matrix. So the velocity which we will record from the seismic wave which will go through this rock is actually the bulk velocity, which is a combination of the velocity in the solid part or the rock matrix and the velocity of the seismic wave in the pore part, or in the pore fluids, or the fluids which are saturating the pores. And at the end, we will have the bulk velocity, which is a function of the velocity of the fluid and the velocity of the matrix. And the porosity is also um, part of the equation. The same thing for density. So the bulk density, which we can record from the rock, is actually a function of the density of the fluid and density of the matrix of the rock. So now we will see the factors and the conditions which will affect the velocities, because we will need this information in order to be able to distinguish different types of factors, different types of fluids, different types of lithologies from our recording. Because as we have done already in the previous lectures, we see what kind of factors are affecting the measurements, and based on that we can interpret our information or our observation or our logs. So it's the same thing here. We see here that the velocity is changing with fluid type. So in the gas, the velocity is low, and it will increase with oil and will increase with water. Why is that? Because the bulk modulus of the gas is weaker compared to the one of the oil, and the one of the oil is weaker compared to the water, and the density also, they are different. So but actually the bulk modulus is dominating the effect of the fluid. In terms of lithology, we see that the velocity is changing also with the lithology type. In the coal, we have the low velocity, and sandstone is larger, and limestone is larger, dolomite is the largest. And it will change also in function of depth and or age. the more the rock is getting deeper, the more the velocity will increase because of compaction and consolidation and cementation. Also, the velocity will change with the saturation and the fluid type. If we have a rock which is saturated with fluids, with different types of fluid, we see that the more the gas will increase, the more the velocity will get down. The velocity also will change with the porosity, and it's inversely linear with the porosity. So the more the rock is porous, the less is the velocity. And it will increase also with the cementation. The more the rock is cemented, the more there is connection between rocks, the more the velocity will be very high. With the pore pressure, it will decrease. With the overburden, pressure will increase. And with the shale ratio or the shale content will increase. In clean sand, the velocity will be different. And when we have shaly sand and then sandy shale and then clean sand, we will have different velocities. So we see here from the clean shale to clean sand, we have a large variation between the velocity. And also, if we can have access to the elastic properties which we have seen previously, then we can extract more properties. If we have, for example, the shear modulus and the bulk modulus, we can extract the Young modulus, we can extract the Poisson ratio, we can extract the lambda or the second Lamé parameter. If we have, for example, the Young modulus and the Poisson ratio, we can extract the shear modulus, we can extract the bulk modulus and Lamé parameter. So having at least two parameters will help us to have access to more and more parameters. And this is very important and very useful because we will see that most of the time we will need to have at least P wave and S wave. If we have P wave and S wave, then we can have access to many of those parameters. We will take now Poisson ratio as and VPVS as an example of the discrimination between different types of rocks and different types of fluids. Because if we have the VP and the VS, or the velocity of the P wave and the velocity of the S wave logs, so if I have P wave log and I have the S wave log, then I will be able to calculate the VPVS ratio, and I will be able to calculate the Poisson ratio, since the Poisson ratio, as I have mentioned already, is nothing but a combination of VP and VS. So now let's try to use Poisson ratio and VPVS in order to extract properties about the fluid and about the lithology of the rock. The Poisson ratio of a rock is actually depending on the solid rock material and also the volume and the shape of the pore space, and also the fluid which is saturating the rocks. So quartz rich rocks tend to have a low velocity ratio and Poisson ratio than carbonate rich rocks. In clastic brine saturated rocks of a given lithology, the Poisson ratio usually will increase with increasing porosity. But poorly consolidated and brine saturated rocks or soft rocks, they have high Poisson ratio, but hydrocarbons or gas saturated zones or reservoirs or sandstones, they have theoretically lower Poisson ratio. So having low VPVS and low Poisson ratio, and many times is a very good indication of presence of hydrocarbons. Now we will see the petrophysics, or the relationship between petrophysics and rock physics. We will try to move from one to another and combine one with another. So we have already seen the different types of petrophysical properties and uh, different types of logging and different types of tools and properties which are derived from well logging, and all those properties which we have extracted, they are actually part of petrophysics. Rock physics is something different. Rock physics describes actually reservoir rock by physical properties such as porosity, rigidity, compressibilities. Uh, these properties, they are actually causing changes, and they are affecting the seismic waves. So from the seismic waves, we will try to extract the same properties which we have extracted already from the different logging tools in petrophysics or in the well logging. So it means we will have another way or another tool to extract the reservoir property, not from the well logs and not from the petrophysical properties like the density porosity, neutron porosity, from, for example, the density log, but we will try to extract fluid type and lithology type with the help of seismic and elastic properties this time. Now let's try to compare them. Rock physics actually uses sonic logs, density, and shear wave, or the S wave. So we are using P wave, S wave, and density only. But in petrophysics, we are using all kind of logs which we have seen in the previous lectures and throughout the semester. The rock physics will try to establish a relationship between the P wave and S wave in order to estimate and in order to calculate and to have access to different types of um, properties or elastic properties or elastic moduli or modulus. We'll try to estimate the bulk modulus, shear modulus, the pore fluid, porosity, pressure, all those properties. We try to extract them only from VP, VS, and density. But in the petrophysics, we will try to extract other types of properties with the help of different types of logs. Rock physics will talk about velocities and elastic parameters because they are the link um, between physical rock properties and seismic expressions. But petrophysics, they are generally less related and concerned with seismic. So we will not talk about seismic properties and elastic properties in petrophysics. And also the rock physics, they are actually of interest to the geophysicists. So geophysicists, they are using information and they are interpreting them and they are using them for different purposes. But petrophysics or petrophysical properties and petrophysics in general is the concern or is the interest of petroleum engineers, geologists, and also geophysicists. So let's now define some recent techniques in rock physics and how they are used to discriminate between different types of lithologies and different types of reservoirs and reservoir lithology and fluids. In the 2003, there was a technique was published which aimed at defining and discriminating between fluid types in reservoirs and lithologies of geological formations with the help of only elastic properties. This technique or this method is called rock physics template or the RPT, and now is very commonly used in many software packages, including Hamson Russell and I'm not sure about Petrel um, and Techlog. So with the help of this RPT, we can discriminate between fluid type and lithology type only by cross-plotting the VPVS against the acoustic impedance. Acoustic impedance is nothing but the density times the velocity of the P wave. And here we have the VP to the VS, or the ratio of the VPVS. If we can cross-plot the logs, or these two parameters, VPVS log and the acoustic impedance log, which is from the density times the velocity, we will be able to distinguish between different types of reservoirs, different types of fluids. We can isolate fluid which will go to the fluid corner. So most of the fluid, they will have low VPVS and low acoustic impedance. We'll be able to discriminate between sandstone or quartz, solid trend, and clay mineral or shale trend. We will be able also to distinguish between the deposition effect and the burial effect, and between the pressure effect. We will be able to see also the 100% brine saturated sandstone trend, and we will try to isolate it from the fluid or the other types of fluids. So this will bring to your mind what we have done in the well logging and in the interpretation techniques, where we were trying to isolate the hydrocarbon from the brine saturated zones by supposing the water saturated zones as normal case, or the normal or the background, and any deviation from that will be due to hydrocarbons. We see here at the deposition stage, sediments, they have very large VPVS and very small acoustic impedance. Why? Because we are supposing that the sediment, they are deposited in the water or in the fluid. So what is happening here, we have very large VPVS, since the VS is almost or is zero, so the VP is there, but VP over VS will go to the infinity. With the compaction and with the increase of the sediments, the VPVS will get down, and with the compaction will get lower and lower, and this will increase the acoustic impedance. So the acoustic impedance will increase with the decreasing VPVS, but with the presence of hydrocarbons, when hydrocarbons will be present in the rock, the hydrocarbons actually will try to deviate from that trend. So we will be having low VPVS. So we will move to the low VPVS, and we will move also to the low acoustic impedance. So compaction will take it down and will lower down the VPVS and increase the acoustic impedance, but the fluid presence will actually try to reduce both of them. So here the hydrocarbon will be shifted and will be going to the what we call the hydrocarbon corner. The presence of shale will actually increase the will increase also the VPVS, and the presence of fluid will reduce it again. And in most of the cases, unfortunately, we will have both shaly reservoirs, shaly sand reservoirs. So the shale will try to increase it, and the hydrocarbon will decrease it. So the shale will be all the time with us, like what we have done in the previous lectures, especially in the interpretation techniques. We have seen that shale all the time is causing trouble for us in the interpretation. So here we'll be having the same thing. So actually, what we will be doing, we will be trying to see the behavior of the VPVS in front of shale and in front of the sand. And when the shale is absent, we will have a very low VPVS. And when we will have pure shale, we will have large, or we will have increase in VPVS. And when we will have hydrocarbon or gas saturated zones, we will have very low VPVS. Now let's move to seismic properties of the rocks, the amplitudes and the impedance. So the acoustic impedance of the rock is actually a measure of the resistance or the opposition of a rock to the acoustic energy which is traveling through this rock, and usually is expressed in function of density and velocity, or the density times the velocity. Seismic amplitude is just a measure of the contrast in impedance between two geological layers. And so if we have the impedance of both layers, or all the layers, we can simply calculate the contrast or the difference between every consecutive geological layers impedances. Then this will define for us the reflection coefficient. So, and this is actually what we are recording in seismic. So seismic methods, especially the reflection method, is measuring actually nothing but the contrast in acoustic impedance between geological formations. They are looking different than the logs. So for example, this one is a reflection coefficient from logs, and this one is a reflection coefficient or seismic amplitude from geophone, or from the surface. They are different because of the resolution, because the geophones which we are recording and we are using in the surface, they are recording the data at very low frequency band compared to the logging tools which we are using in logging, or in the sonic and the density logging. So in the sonic and density logging, we have a very high frequency logging, so we can have a very high resolution and very high details, and too much details for very thin beds, for very small intervals. But geophones on the ground, actually, they are recording almost, and it's basically or theoretically it's the same information, but since we have very low frequency band, so we are recording a very smooth information or signal or log compared to the one which we are recording at the borehole. So it's a matter of resolution, and it's a matter of frequency of the receiver which we are using to record the information. But the advantage of the seismic is that we can have many logs like that one. We have many logs which can be recorded at many points without drilling and without a need for a well. So we can record and we can have this information by just putting geophones on the ground. And if we have many geophones, millions of geophones on the ground, we will have similar recording or similar measurements, which is a kind of smooth measurement of what we are recording at the well location using the well logging tools. So this is actually is very helpful and very useful in the way we can think about the integration between the seismic and the well logs. So for example, these are information which are recorded by logging tools. We have here the P-wave log or the sonic log, which we have already seen in the porosity logs. We have density here. So from the two logs, we can calculate and we can estimate or we can determine the porosity, the impedance by multiplying this one by this one. We can have the impedance. From the impedance, we can simply calculate the difference over the sum of each impedance at every depth sample. Then we can have the reflection coefficient. So this is the reflection coefficient. If we try to smooth it, then it will give us exactly the seismic trace. So this is a seismic trace. But basically, what do we have in the field, and what do we have in seismic, and what do we have in seismic surveys? We have seismic traces from geophones which are on the ground. So we will try to do the opposite. We will try to use this trace in order to get back to the reflection coefficient. From the reflection coefficient, we try to get back to the impedance. And if we can get back to the impedance, we can get back to the P wave and we can get back to the density. So it will be like what? It will be like we have drilled wells at every location where we have this kind of seismic trace. Okay? So if we could do that, we will be able to extract many informations like the one which we have extracted at the well location. So if I have density log, I have velocity log, then I will be able to calculate the bulk modulus from this equation, and I will be able to calculate the rigidity term or the shear modulus from this equation, and I will be able to calculate the Poisson ratio from this equation, and I will be able to calculate the Young modulus from this equation. But if I have parameters which are extracted from the seismic, because seismic, as I have mentioned, will provide us most of the time with impedances, but the not the exact velocities and exact densities. So most of the time, what we can get from the seismic traces, we can get the reflection coefficient. Reflection coefficient we can, by improving the resolution and removing the wavelet, we can get the acoustic impedance. And if I get the acoustic impedance, then I will be able to estimate the P wave and density. But usually in seismic, we stop at this stage. We stop at the acoustic impedance because it's not easy to get the correct density from the seismic. We can get it actually, but it's not that reliable. So we stop here at the acoustic impedance. So that's why most of the time when we try to extract any of the elastic moduli from the seismic, usually we use impedances rather than the velocities, like the one which we're using in the logs. So in seismic, or using the seismic data, if we have seismic data, usually we will have impedance, which is rho v. So from the rho v, or from the impedances, I will be able to calculate rho, or the density, times the bulk modulus, which will be somehow or more or less the same as the one which we get from the logs. The same thing for the Young modulus, for the shear modulus. So I will use the impedance of the shear wave, and in the Poisson ratio, because the in we have the density in the denominator and in the numerator, so it will go with each other. So the density from up will go with density from the down term, And then we'll have Poisson ratio, which will be the same thing. So the Poisson ratio, if we extract it from the logs or from the impedances, from the velocities or from the impedances, is actually the same thing. For the Young modulus, I will be also using the impedances instead of the velocities, and I will have access to the Young modulus, and I will be able to interpret it in a way that is similar to the one which I can do at the well location. So now let's suppose I have now the rigidity term from the seismic, and I have the bulk modulus, and I have the Poisson ratio. How this will help me to discriminate between different types of fluids and different types of lithologies. If I have sand with gas, I will expect to have high rigidity term. Why? Because the quartz which are forming the sand, they are much rigid compared to the clay which is forming the shale. So I will expect to have high rigidity, but I will have low bulk modulus. Why? Because we have already mentioned that the bulk modulus is the inverse of the compressibility, because the gas is compressible. So I will have high compressibility. So it means I will have a low bulk modulus, and I will have a low Poisson ratio, as we have already seen. When we have sand with brine or with water, we will have high rigidity, because the rigidity or the mu term is actually associated with the matrix or the lithology, not the fluid. So it will follow the sand, but not the fluid. The bulk modulus, I will have high bulk modulus. Why? Because here the water is less compressible than the gas. So I will expect to have a high bulk modulus. For the Poisson ratio, we have already seen that in the presence of water, we will have a large Poisson ratio. For shale with gas, we will have low rigidity term. Why? Because the shale, they are less rigid than the sand. And because of the presence of gas, I will have low bulk modulus. And because of the gas, I have low Poisson ratio. In shale with brine, I will have almost the opposite. So now we will try to estimate the porosity from the seismic. In the porosity logs, we have seen that we can estimate the porosity from the neutron or from the sonic log or from the density log. In this case of the seismic interpretation or seismic quantitative interpretation or seismic integration with well logs, usually we try to estimate the porosity from the acoustic impedance. So we are combining the density and the sonic in the acoustic impedance log, and we cross plot them against each other. Then we'll have an equation which will define the porosity in function of the acoustic impedance. Okay, so this one is another porosity which is different than the ones which we have seen, or it's a different way actually to estimate the porosity. So now we have the porosity, which is a function of acoustic impedance, and from the seismic, since we already have the acoustic impedance and we extract it from the seismic, as we have mentioned earlier. So earlier we have mentioned that if I have seismic trace, from this seismic trace I can do the inversion in order to extract the elastic properties or the coefficient or reflection coefficient and the impedance from my seismic. So I will do that for all the traces in my seismic. So this is my seismic. I will extract, or I will use all my seismic section, and all the traces in my seismic section, I will convert them to acoustic impedance section using the seismic conversion. And if I can do that, I can convert all my seismic section to acoustic impedance section like that one. Then what I will do, I will just use the relationship between my porosity and my acoustic impedance, which I have estimated from my wells. So I will use this equation, and this equation will help me to convert all this acoustic impedance and to put it here and to estimate the porosity section. So if I use this equation and I will substitute the acoustic impedance section here, I will have the porosity section. So it will be a porosity section, not a porosity log. And it's like what? It's like a porosity log at every point. So this is the advantage of having the seismic, or the advantage of integrating the well logs with the seismic. So, and if I have now the porosity and I have the saturation, which I have estimated at my my well location, I will be able to estimate my reserve, because the reserve, it has to be estimated over the whole reservoir area. And what do we have in the reserve equation? The reserve estimate equation, it contains the dimension of the reservoir. From where I can get the dimension of the reservoir? I need the thickness of the reservoir, which is H, and I need the porosity, and I need the area. From where I can get the area? The area, usually I will need seismic in order to provide me and to give me the area over which the reservoir is mapped and is identified or is delineated. The other, and also I can estimate the saturation from the resistivity log. And then if I have that, then I will be able to estimate my my reserve with the help of the seismic and with the help of the logs, which I have integrated. So lastly, we will see some applications and some real examples. So in this example, we have case study from Columbus Basin in the US. So what do we have here? We have seismic section. In this seismic section, we have gas sand, and we have silt or brine saturated silt, and we have tight silt with gas show. The seismic is showing them quite similar, and we cannot interpret them using the seismic alone. So what we have done and what we can do, the author, what they have done, they have actually inverted and they have estimated the incompressibility, and they have estimated the rigidity from the seismic. So once they could estimate the incompressibility and the rigidity has given them where the sand is located. So they could identify the sand and separate it from the silt. So the silt is here and the sand is here. And the incompressibility, which they could estimate from the equation which we have seen previously, it has shown them where we have low incompressibility, which is indicative of gas. So the incompressibility, it will indicate, and it will show the gas interval, and the rigidity will indicate the sand interval and the silt, or the matrix in general. Another case from Alberta, Canada. So we have the seismic here. So here we have seismic traces at every location. We have a couple of seismic traces which are over the reservoir zone. The reservoir zone is here. We have one single log here. This log, we will try to integrate it with the seismic, and we try to extend the information which we can derive from this log to areas which do not contain logs. So what we will do, we have the P wave, and we have the S wave, we have a density log, we have the Poisson ratio, and we have the VPVS. All these logs, they are estimated only at the reservoir or at the well location. So what we will do, we will try to extract the logs. These logs, we try to extract them from the seismic as we have seen previously. So if I have my logs, if I have my seismic traces, from the traces, I will do the inversion and I will try to extract the acoustic impedance, reflection coefficient, and the acoustic impedance, and then P waves and S waves. If I can have the P wave and S wave from the seismic, because I can find the relationship between them. Then if I can have the VP, VS, and the VP and the VS, and the P wave impedance and the S wave impedance and the density, then I will be able to extract and to calculate those elastic properties, and I will be able to extract, for example, the Poisson ratio, the Young modulus, the shear modulus. And at the end, I will be having a Poisson ratio section. So it's not a Poisson ratio. This one is a Poisson ratio log, and this one is Poisson ratio section, which will show me the extension of the reservoir, and it shows me also the extension of the gas, because as we have seen, the gas is characterized by very low acoustic, very low Poisson ratio, and we can see it here. So the integration between the well logs and between the properties or the elastic properties which are derived from the seismic could help me to delineate and to extend to delineate and to track and to see the extension of the reservoir from uh, the right to the left, and to get a very good correlation between my information from the logs and from my information from my seismic. And thank you for attention. And if you have any question, please try to email me and contact me, and I will be happy to help you and to explain any ambiguity that it might rise from the the material which is expressed and explained throughout the lecture. Thank you.